Hello guys, and very welcome to this exciting tutorial series, Mastering Houdini Destruction Simplified. It contains 3 parts: Introduction to RBD, the second one is Simulating Debris, and the last one, Introduction to Pyro. What is our goal of this tutorial? To provide you from wasting your time for searching a right tutorial. Because the time is most valuable resource, better spend this time with your family, with your friends, with your children. Our motto is, if you cannot explain your ideas and goals to a 6-year-old child, then you probably don't understand it yourself. This saying comes from Albert Einstein. What you'll learn in this tutorial, whether you're a beginner or looking to refine your skills, I'll walk you through the essential elements of destruction simulation. We will cover all critical components needed to master destruction effects. The first part, what you need for RBD simulation. Maybe you know the scenario. If you did a tutorial and after a couple months, you have to go back to the topic and you don't remember what you did. What I do in this tutorial, I will give you only a couple things to memorize, and you will be able, after month and month, just come back to your topic very, very quickly. What are procedures of this tutorial? We will explore physical attributes here. We will implement the fracture. We'll talk about activation, the fractured object, and we will set proper collision, because this is very crucial task for every RBD simulation. We'll apply forces like a pop drag and pop spin drag. We'll animate our collider along a path. We will simulate the proxy objects, cache the points representing these proxy objects, and then we transfer this point cache to high resolution geometry. Okay, let's jump inside Houdini and start. Point 1 is setting up RBD packed objects. What is a packed object? The packed object is the object or geometry represented with 1 point. Let's see how can we achieve this. I created here a simple setup. What I do here, I'm creating these points, and I can specify the width and height of the wall. And what I do here, I just copy and this geometry on these points. And what I did also, I just transform it a little bit, and I just bring these guys a little bit up. And I pack it with a pack sub. Let's see the result. Just ignore for now this setup, because I will go through in details and I will explain you how to create this setup. If you look at the result now, this whole brick wall is behaving like one big object. Let's move on to the second point. The second point is ensuring unique name on the point. Let's see what does it mean. Now we have one big wall represented by 1 point. Let's give first a name. I will just create name here. I bring it to points. I explain you why later. And I say this will be our brick. Now you see our solver is happy because we have 1 point, 1 geometry, 1 name. Now imagine the scenario you like to have separated wall. That means we have to have for each separated geometry its own point. How can we achieve this? With for each connected piece sub, I connect it before packing, because we like to pack it inside this loop. What this guy is actually doing is looking for connectivity of these bricks and create this class attribute. If you look here carefully on a geometry spreadsheet on a primitive, you have this class attribute going from 0 to 55. That means we have 56 points or 56 loops here, because as you already know, we have here 56 points created or bricks created. And now if you activate this single pass, you can do for each point operation. Let's pack it. I create a pack. And also, as you see here, I would create also the name. I just copy this guy and bring it here. And I create also the name here. Now we have 56 points here, name attribute, but only one unique name, not per each point here or for each packed geometry. Now let's see if we just bring this guy inside our solver. You will see now we have this result. It's fine. It's working, kind of. But if you go inside, you will see your solver is complaining. Let's see why it's not complaining. Yeah, it's complaining because it says, hey, your name object contains duplicate values, name attribute. This solver now has a problem to recognize each object here. It looks fine now, but if you get some complicated geometry, you'll get also very strange behavior. Let's see how we can just create unique name for every brick, because as you already saw here, every name is the same for every packed geometry. Okay, let's see how to fix this problem. First, I like to disable this name attribute because this is the same for every packed geometry here. And I will create outside with a wrangle the brick name based on a point number. I would say as at name on point level. We use here printf function, vex function. What this printf function does is just taking this string, I just say here brick, and underscore, and I put now the placeholder for the integer, because integer is a point number, because we have no decimal ending there, because point number is 1, 2, 3, 4, 5, 6, 7. And I use percentage small d. This is placeholder for integer. And what I'm saying here, please replace this guy with the point number. As you already know, the ptnum is global Houdini vex variable. It stays for point number. We have here 56 points, and this guy will just go from 0 to 55. And if you look at your geometry spreadsheet, now we have your brick from 0 to 55. And now if you look inside your setup here, if we just rewind and play, you see now we have our bricks here, and also our solver is happy. Let's look at the point number 3. Using RBD point level, for RBDs we have to use a point level, and for constraints a primitive level. We will not touch constraints in this tutorial, but for you to know, if you use a constraints, you have to think this way. Everything with RBD is on a points, and everything with constraints is on the primitives. That's why it's very important that you at the beginning work this way. You create a name for RBD on the points. Otherwise, it will not work with constraints. Let's see what I mean here. You see, we created here the name on the points. And also here. on the points. If you see, if I change it to primitives, I just copy this guy here. I just comment it out and I will say this is not, I change it to primitives and we have here not pt num, we have here prim num. I just rename it to name. And if you look at this, now we have the name on the primitives, also unique names. And it also will work with the solver without any problems. It will not complain. But as long as you bring your constraints here, for constraints, because the constraints are working this way, you have a 2 points and the line. I will just create a line for you. This will be your line. Let's see. What a constraint is a primitive connecting two packed objects. And take in consideration the name of this packed object. And this way, this constraint just hold this two packed object together. It is very important that your name is on the points. This way, this line knows, okay, this point belong to this packed object and this point belong to this packed object. And that's why it holds these guys together. But if your name is on the primitive, it doesn't know about which name you have on the point. Let's look at the node. Bullet solver does not accept volume collision. In Houdini, we have two types of collision, a surface collision and volume collision. The volume collision is very precise, very quick, and is very popular to use. I will say this because this is new method. This is very quick and very precise. But in our case, it will not work. I will show you why. You will see here, I use this geometry as a collision, and we will expect that our brick wall just fall down inside this area. I create with collision source my collision object. On one side, I have the VDB representation of the collision. On this side, I have a geometry. And if you go inside here, I set it up here. Don't worry if you don't understand this. I will show you in detail how to do this. And if you just activate your collision here, you would see that I just show first my volume collision. Here you see on this collision object, I have this set up here. And if I show my volume collision, it's looking like this. I just turn off my bullet data here. Okay, you see my volume collision looks like this. It's everything fine. And we're expecting that this wall will just go down to this area. Let's see. You see, this volume collision doesn't work for our bullet data. You see, the bullet data has its own collision. That's why I just go back here, I deactivate the volume collision. I go to bullet data because this is a bullet solver, and I activate the collision here. And you see, even the collision here is, the volume collision looks good. It works with this collision here. And you see, this is our collision. If you want to make it better working here, you have to change this guy to concave, and yeah, now you will have your expected behavior. To better memorize these points and this node, let's build our RBD structure, and then we'll go back and look and explore these physical attributes. Look at our instruction. We need setting up RBD packed object. We have to have first our geometry. Let's create geometry container. I just rename it to tutorial. I dive inside and I will create here the grid. It will be 20 by 20. I will have here 100 rows and columns, and I create a noise. Mountain. And let's do the element size to 4 here to get something like a terrain here. And I will use here the volume, extrude volume. I set depth to 0.5 and I bring my volume a bit up with the transform node. Transform, and I like to copy and paste this parameter. I just copy this, or you can, maybe I put first 0.5 here, and I copy this guy and put it here, paste relative reference, and I put minus here. Now you see we have something like this. I like to have it on a grid here. That's why I like to put a little bit offset here. Maybe I would say here. I just transform it with another transform node a bit up. You can go with space 3 and just look at the values here. You see, I like to go up a little bit, something like this. Okay, maybe a little bit up, because we have to have some place to have a gravity force putting down our terrain. Okay, great. Now let's just scatter a couple points here and do a fracture. I will use here the material fracture from Houdini, and let's see how we can do this. Just type a material fracture, and you will see here we have RBD material fracture. Don't connect it because it's very, very slow, this node. It's doing a very good job, but this is very, very slow. What I do first, I just delete this second iteration because we don't need this iteration. And by default, I use here concrete and scatter points. We have here 5. That will be enough for the beginning to understand the setup, because we will rebuild it. Just connect these guys here, or this guy, and let calculate. And you see now you have something like this. To see better what this RBD fracture does, we will use here exploded view. And you see if you connect it here, you will get something like this. But if you look carefully, here is something very, very boring here. Let's create a bit interesting chunks here. What you can do here, if you go to material fracture, you can go to details and you can activate here these two guys here. It will create some jaggedness on the edges and also inside faces. It will take a little bit more time here. And you see now you have some jaggedness on the faces and also interior details. It's looking now better. Okay, let's see what this guy is doing. By default, every fracture that Houdini have, for example, we have Voronoi fracture, we have a Boolean fracture, it gives you by default the name attribute on the primitives. That's why you can use this exploded view, because this exploded view uses this name attribute to be able to separate these pieces. If you look, if you now just click on the name attribute, every piece has its own color or its own unique name. If you look at the geometry spreadsheet, you will see you have this piece 0 until piece 4, because we have 5 pieces here. The first one is 0, 1, 2, 3, 4. Okay, great. Now we know that the RBD fracture gives us the name and also fracture it. And also very important thing that this RBD material fracture also does, it gives us 2 components. This guy is our high-res geometry, and this one is a proxy. If you look on this output, it gives you the proxy object. What we will do, we will simulate this proxy object for the performance. We will cache it, and then we will just transfer this simulation on a high-res geometry. Let's look at our instruction. We need now the RBD packed object and with a name attribute owner points. We already have the names owner primitives. Now we have to first pack the object, and we have to promote our name attribute to the points, or create our own name attributes. Let's see how we can do this. Okay, I will use now the pack node, because as you already know, the pack node do 1 point for every, or one point for this whole geometry, but this node has a very good checkbox. You can just say, hey, just look at the name and make for every name one packed object. Now you see, if you don't check this, it will give me a 1 point attribute. But if I check this guy, it will give me 1 point per each piece here. But you have to be very careful here, because this guy just take and swallow the name attribute. If you like to have it down inside your network, you have to transfer this attribute. If you want to use this attribute, or you want to use a name here, you can use it, but I will create my own, because I already show you how I did it, and we will stay with this, because you can rename it to your own naming convention. Okay, now see, I have here 5 points, and now let's create the name on the points. I create a wrangle. I rename it to set name, and I will use here as add name is equal. I will use a sprint f vex function. If you look here on the documentation, it will explain you how it works, but I already show it to you. I just write down now here ground underscore, and I have here %d for the integer, and this will be placeholder for a at ptnum. And you see now, if you look here, you'll get 5 unique names. If you look at your geometry spreadsheet on the points, we have ground 0, 1, 2, 3, and 4. Now we achieve our goal here. We have now the packed objects and also the unique names. If you look here on your information, it's giving you a packed fragments. And now you have a name and also packed fragments. Now we are ready to bring this pack object inside our RBD setup or DOP network, and let's see how we can create this DOP network. First, we need a DOP network. I will name it to RBD sim, and I connect my output here to the first input, and I will dive inside my setup. We need here the RBD packed object. We need here rigid body solver. We need here gravity. And also the merge node. And ground plane, because I like to just drop down my terrain on this ground. What I do here, I connect the ground to the first input and this guy to the output. And now you connect your gravity to the second. It's very important that you have to set up, because otherwise it will not work. And now I just take the RBD packed object and connect it to objects. And I connect the output of the RBD solver to the gravity. You see, now we have our ground here, but we don't have our RBD packed object, because we have to specify the path, or we have to specify the input, because by default it's look for subsource here. What we can do, we can say first content geometry, and you see now you have your terrain. Now if you play your terrain, we just go down and breaks a bit. Let's understand the meaning of this activation. I will create now one attribute that this RBD solver already recognizes. The attribute is active. This is on the points. That's why I can do it after I pack it. I just create another wrangle, and I will just write set active, and let's create this attribute. I would say I add active is equal 0. If it's 0, it means that this object will not move. If you dive inside your setup here and play it, you see there is no simulation. If you set it to 1, it will work now. You see it's doing what we expect it to do. There is a big gotcha of this guy here, because this changes, or this attribute is only recognized on the start, by the start of the simulation. That means if I change this, depends on my frame number, it will not work by default. Let's see how we can fix this problem. Okay, I will create a condition here. First thing you have to do, you have to change your frame range from 1001 to 1241, because this is very important for the production, that we have some pre-roll. Always, if you do any simulation, just start it from 1001. But you have to be careful before you change it here. Please set up your simulation start frame here. Otherwise, you'll wait a long time until it will just go to your simulation. That's why first change it here, and then you can change it here to follow with me with my setup. Okay, what I do here, I will create a condition. I would say if my frame at frame is greater than 1024, set active to 1, otherwise set it to 0. Okay, you see, if you look at your geometry spreadsheet, after, I just look here, it's 0, and after 24, it's becomes a 1. It's working here, but if you look inside your setup, nothing happened. Why? Because, as I already told you, it's recognized it on a first simulation frame, and it's ignore the changes. To be able to get these changes, you have to activate one very important attribute here inside RBD object here, you have to activate override attribute active animated deforming, because I like to override it on a sub level. And now if you look at your simulation, it will just, after 24 frames, it will just, the gravity will pull down our object. Before we move forward, let's look at the physical properties of our RBD packed object. I already prepared for you the dailies. We'll look at the density first. And if you compare the three guys, the objects with higher density behaving heavier. Let's look at the next one. Next one is a rotational stiffness. If you look here, we have rotation stiffness 0.1, 0.5, 10, and 1. Let's compare them. And you see what the rotation stiffness does. Let's look at the other important attribute, the bounce. We have here bounce 0.1, 0.25, 1, and also 0.5. Let's compare them together. You see, the more bounciness you have, the more bounce your object will get. Okay. Okay, that's it for the RBD packed object. Let's first look where we can find these attributes. If you go inside your DOP network on your RBD packed object, under physical tab, you will find the density, rotational stiffness, bounciness, and friction. I forgot about the friction, but the friction is self-explanatory. Only thing that you have to take in consideration that the friction work in conjunction with the ground plane in this case, or conjunction with the other collider object. If, for example, if I put on a ground plane the friction to 0, doesn't matter what I put here, it's just like a multiplier, it will just ignore this friction here. We have to take it in consideration. Okay, now let's see how we can create this setup. First, I will explain you the idea behind the setup, and then we'll build it from scratch. What I did here, I just draw the curve, and I show you now. I have a curve here, and I make this object follow the curve. You see here we have this animation, and this curve or this object acts as a collider and breaks the terrain. Everywhere nearby this curve, I have more fractured pieces than here in the middle or outside. How I achieve this? I just scatter first points on my terrain, and I give a black color to whole points here. On this curve, I gave a white color, and then I transfer the attributes, color attribute, from my curve to my terrain points. And then with this attribute wrangle, I just delete every point far away from the curve here. And I use here the replicate sub for make a bit more points. And then I use these points in my RBD fracture sub to make my scattered geometry. You see, if you look here at exploded view, you see everywhere where nearby the curve I have more fractured pieces. Okay, let's build it from scratch. Let's create our curve and move the breaker geometry along the curve. But before we do this, I like to explain you the very important function, the primiv vex function. What it actually does, it pick a position along the curve and return it. For example, we have a u attribute on a curve. It starts with 0 and ends with 1. What this primiv function does, it just, you have a slider here, you can change a slider, and if you change the slider, it will just take your input number 1, the curve. It will say, okay, this, I just pick the position, you can pick everything, because if you have, for example, the normals, if you have other attribute, velocity, whatever, you can pick or you can sample with this primiv function every attribute along this u attribute of a curve. You change the u attribute with this slider. For example, you'd like to get the position when your u attribute is 0.1. It means that your u attribute goes here, pick a position, and return it. And then we can just take our geometry, or in this case it will be a point because we will pack it, and just bring this geometry or point to this position. If you change it again, it will go to 0.2 or everything in between, and you just grab the position and put your geometry to this place. You can grab whatever attribute you like. If you have here normals or velocities, you can grab or you can sample every attribute you like. Okay, let's see how we can achieve this in practice. First, we have to create a curve. For this, I use the curve node. I just press space 2 and go to the top view. I activate the curve here, and also I just template my terrain. And now I click this button to activate the tool. And now you can just go from here and draw a curve. I like to have something like this. I press enter now and go out of this tool. The curve is a little bit jaggy. That's why I first convert it to NURBS. You see, I just say to NURBS curve. Okay, let's create our breaker geometry. It will be a sphere. I set it to polygons. I transform it in Y to 0.5, and I pack it also, because we would like to have a packed geometry. And now we use our wrangle. I just say move along curve, move along curve. And my geometry goes to the first input and the curve to the second. Let's create first our slider. I will say float because it is float slider. I will say u is equal channel float u. You can just say progress if you like. And now let's set our P attribute, because this P attribute will be the position of this point, because we will already pack it. And we go through points and specify now the position of our one point here. And I say this will be a prim UV function. This is a documentation. It needs the geometry input, attribute you want to sample, then the primitive number, and our UV, this slider. Okay, let's put input number 1 because we like to sample something on a curve. The attribute we like to sample is position. From which primitive? If you look at your curve here, we have only one primitive, and the primitive number is 0. If you look here on your geometry spreadsheet, you have 0. Number 0 of your primitive. That's why I put here a 0. And the last thing is the UV attribute, or U attribute, sorry. And you see now, if you click on this guide to create this progress, you can move your geometry along the curve. If you like to get something more simple, I did a tutorial on YouTube. I provide you with a link in the description, and you can also learn another method of moving the curve along object along the curve. Okay, great. Let's see how we can now scatter points along the curve here and make our fracture. Okay, let's first create the volume out of our terrain. I just press space 1 to get back to my perspective view. And you see, this is my terrain now. Let's create VDB out of it. I just say VDB be from polygons. Why I need the volume here? Because I like to have a points also inside my volume, not only if I scatter it now, it will just scatter the points over the surface. But I like to have something inside too to get a better fracture. That's why I convert my terrain to VDB. We don't need the surface, we need a fog volume. And now I scatter the points here. I just use a scatter node. I just turn off the relax iteration, and I don't need so many points, maybe 100 will do the trick. 100. Okay. And now I like to just, maybe let's do 200. Okay, now it's good. And now I like to just make the color of these points black. Just go back and set the color here. Oops. I use a black color here, and on this curve side, I use the color and set it to white. And I like to now transfer the color from the curve to the points of my terrain. I use here attribute transfer. And you see by default, the distance threshold is very high. And by default, it's already transferring the color. You can, if you want, you can put the color also here because we're working with points. And a condition you see, now I just wanna pick only color or only the points. They are nearby the curve here. You can also play with the scatter here, go maybe for 300. And you see now we have this. Now I like to delete everything black and just keep the white points. Let's see how we can do this. I will use here the blast node. I just say blast. I go over the points. I will create here a slider. I will say this will be a threshold. The range will be 0 to 1. What I actually like to do, I will say just just look at the red value of the points. If this red value is less than some threshold, just delete it. Because as you already know, the white color has three components: red RGB, red, green, blue, and all the components are 1. If you have a black color, this will be a 0. And now I can just do a threshold here. I show you one little trick that you also have the gradients here inside, gradients of color. If you, for example, go here to transfer and make the gradient here, you see some points are some kind of gray here. And now what I say here, I'm telling if at CD, because this CD is recognized by Houdini, this is global variable, vex variable for the color. With a point, I get this red component. And I say, if this red component is less than this guy here, I just copy this parameter, I click it here and I paste it. Paste relative reference. If is the case, just delete it. You see now, you can just specify which point you want to delete. You see now we stay with white points. And if you can go here, you can just make them a little bit. It's just like a radius for searching here. Now you see we have these points. You can play with these values. If you want to learn about other methods, I have also another tutorials on YouTube. I provide you with a link if you want to learn a different method that do the same thing. You're welcome. Okay, let's see how we can now replicate, because we have a couple points here, but it will be better to have a little bit more points for our fracture. And let's see how we can achieve this. Okay, I use here at a point replicate node. What this node does, it just take one point and make a replication inside a shape. If you look here, it replicates 100 points inside the box. And you also have a noise. If you like to add a noise, you can use noise here. I like to have maybe 10 points. And for shape, maybe I will use here the sphere to make some. And you can do a little bit noise if you like. And there is, I think, also, no, there is a seat. You can change the seat if you like. Okay, now we have our points. And what we can do now, because we specify here in our RBD fracture, we specify scatter points here. What I like to do now, I like to just disable this attribute and enable input points. And if you look carefully on your RBD fracture, the last input is extra Voronoi fracture points. Disable. You have to press escape because this node is very, very slow. And I just connect this guy here and press here. And it have to calculate now. You have to activate your input points. And I'll go back to you when it's finished. Okay, it took about 1.5 minutes on my computer. And you see if you click now or on exploded view, I disable my, okay. And also the color, because you have here the name attribute. And you see now we have this interesting pattern along the curve here. And this is our proxy. And if you look at your, you see the high-res geometry. It's looking very good here. Now what I like to do, I like to cache it, because I don't want to wait every time when I just recook my network. That's why I highly recommend to cache this outputs. Let's see how we can do this. If you work in a production, it's very important that you set your environment variables. I already did it. I show you how to do this for your setup. If you go to Edit and under Aliases and Variables, in the Variable tab, you get this variables. As you see here, I already set my cache variable pointing to this RBD destruction. And I have also the other variables. For example, if I have render, my renders goes here, renders go here, and also I have the source somewhere. No, I don't have a source. Normally I have also the source variable. Let's see how we can set it. What you have to do if you don't have the variable, just write down the name of your variable. In my case, I just wrote cache. You can just write whatever you want here. And you just put here the path of your drive or would like to have this. And don't forget to swap this backward slashes to forward slashes, because it's better to Python to understand this. And now if I write somewhere $cache, it will point to this directory. Okay, let's create two caches, one for proxy and one for the high res. I will use here the file cache node. I rename this file cache to high res. I just say ground high. And I will use this one also here. It will be our ground proxy. Let's change something here. This is not time dependent because I like to have only one frame here. And what I do here, I would say I like to have my $cache here. You see it's already there because I set it up. And I use here $OS. And I don't need any variation. If you like to have some variation for your supervisor or for your production, just make a variation here. I just disable this. And now it's also very important if you're working with VDBs, use a VDB here. But in this case, we stay for Houdini vanilla extension here. And I just say here, save to disk. Okay, now it's saved. Don't forget to do the same here. You just can copy and paste or just write down here. I just do the same here. I just do cache. I just do $S. It's not time dependent. I don't need any variation. And I say here, save to disk. And now you see you have your fracture now ready to go. Okay, let's see how we can bring this geometry inside the dot network. Okay, we already did our setup here. Everything what we have to do, we have to bring our collision geometry inside our dot network, and I will show you how to do this. And we will also set our proper collision and the forces. Let's see how we can do this. As you already know, we have our collider geometry here. I connect output of this collider geometry to the second input of my dot network. And let's dive inside and set up the collision here. I just go inside. I just go back. And you see now we have our new fracture. If you look now we have more points. That's why it's take a little bit time, but it's it is working now. What I like to do here, I like to bring the static object here. Static object is responsible for the collision. I like to rename this object here. That will be my ground or terrain. And this will be our breaker. Create a merge node and just merge these guys. And what I'd like to do here, you like to specify your sub path here. You need a null object here because as you see here we have a possibility to get the first content geometry, but here not. But I show you one trick. You can use sub input path. For this you have to use these backticks, and you just say here op input path, open the brackets, and you have here explanation how to use it. For example, we like to have this will be a name and index of an input. And you see it's giving me here some information how to use it. I will create here. That means use the itself, and I like to have here 1 because the numeration beginning from 0, and our second input is number 1. Let's see if it's working now. I didn't see my breaker here. Okay, you have to use the 2 points here. Sorry about this. And now we have the breaker here. You have your terrain, you have your breaker, you have to activate your output. The problem that I have here is my breaker is inside the geometry. I don't know why, because actually, where's my, okay, I know why. Because our slider now is not on a 0, because we have to animate the slider. I show you how to animate this. Let's see first. In our dot network is everything okay. Now you see if you activate your geometry, and you see we have our breaker somewhere. Where is my breaker? Here. Let's see. Perfect. It's working. Maybe you can try to bring your geometry a little bit up. You have to just transform your curve. Let's see how to do this. I will just take the curve and I put the transform here. I just use transform node, put it here, and maybe go a little bit 0.25. And now don't forget to save, because the more nodes you have, the more is possibility that Houdini crashes. Okay, now you see it's somewhere here. I like to bring it a little bit back maybe, because it's better not to have any collision on the frame 1 here to provide you from troubles. Let's see how we can do this. I just transform a little bit back, maybe the whole curve here. A little bit. You see here transfer. I just put maybe 0.5 here, and I put the curve a little bit back here, maybe 0.3. And you see now, if you look in your dot network, we have something like this. Great, now let's see how to set up the collisions. Okay, first let's look at the breaker here. If you select your breaker and you go inside the collision tab, and we use here bullet data because we're working with a bullet, and this is a representation of geometry. Let's see how the solver calculate the collision. If you go here and you show your guide geometry, you see it's fine. I will give you one very important tip. Never let this geometry in a viewport. It will slow down your simulation quite a bit. That's why check first if everything fine, just disable it. Let's see now the collision of our terrain. Select this object, the same thing, bullet data. Just disable this geometry, show guides, and you see it's some kind of good, but you can do it better. Because if you look, there is some roundness around this setup here. That's why you go here to collision padding and just put a couple zeros here. And you see now it's more precise than it was before. Don't forget to uncheck it. And let's simulate and see the result. Okay, it's falling down, it's fine, but we have no animation on our breaker object. Let's see how we can achieve this. Let's move on to our move along the curve wrangle and make an animation here. You can animate it as you do with the keyframes, but I show you a little trick that I always use. I will use expression here, a fit expression, and I will use also start and end frame. First, I like to create my start and end frame variables. What you can do here, you can write here float, start, or start, and it will be channel F start. Okay, I just copy and paste it, and I rename it to end. You see we use end here, and if you click here, you will get your start and end. I like to start from, I don't know, 24, and I like to have it maybe until 80 or something, because you can change it procedurally here. And what I like to do here, I would say here fit 01, oh no, fit expression. What the fit does is to take a value and fit it between min and max input and min and max output. For example, I like to take my frame, I just write down here, add frame, maybe I just write for you a little bit bigger here. Okay, I would say just take this value, take my min and max, in this case it will be start and end. Let's just save it. I will use here copy and paste. That's why I just will do it here. I just copy this parameter and I click here after the comma and I paste relative reference. I do comma again, copy this parameter and paste it here. Now I go to, if you press Alt E, it will open the external editor, and we will say here 0 to 1. What it actually does, it take a frame number and look at your start and end frame. For example, if 1024 will be a 0 and 1080 it will be 1, and it will interpolate between. That means it just fit this start and end to these values here. Press apply, And now if you click here and look at your animation, you see now it is running here. You have to disable your simulation because it tried to simulate too. That's why it's so slow. Now you see after 24, I think it's a bit too quick, but you can put here 120 or something. And now you see it will be a little bit slower. Perfect. It's great. Now let's see what's happened inside our DOP network. Don't forget to activate this one. And now you see what it's doing here. And you see our object is not moving. Why? Because you have to activate a very important attribute here under the static object, because as I told you, now it's just take the shape on a first simulation frame and doesn't do anything. Because we have to check this use deforming geometry. And now you see, now we have some breaking geometry. Okay, great. Now we have an issue here because as you see here, after frame 24, everything is falling down. What we'd like to have, only the pieces along this road will be activated, and not just like activated on a frame 24. It will take in consideration our movement or movement of our breaker, and when our breaker achieve a place here, it will be activated. Let's see how can we achieve this. First, I'd like to explain you how this setup works, and then we will build it from scratch. As you see here, first, we set our active attribute to 0. This is our proxy cache geometry. And then what we do here, we just take our curve, or sorry, not curve, we'll take our packed sphere geometry and just transfer the attribute here. Because what we're transferring here, you see this object is active set to 1. That means now we're just transferring the active attribute from this point to these points of our proxy geometry. As we already know, the packed geometry represented with the points. That's why we can just transfer our active attribute from our packed geometry to our packed fractured proxies. Okay, let's see how to do this. This is our fractured proxy, and this will set this active attribute based on a frame. Now what I like to do, I set the active attribute to 0. Now these all fractured pieces will not move. And you see this is our breaker geometry. It goes now to the second input. If you click with the Alt, you will get a point here, and I just create a wrangle now because I like to have I think you can connect it here. I like to have the active. I just copy this, paste it here. It will be active to 1, and here set active to 0. And I just copy this whole code here and bring it here. And I set it to 1. And now I like to transfer the attribute from the breaker point, because we have only one point here, to these points. We have, I don't know, 870 points. I use here attribute transfer or transfer attribute. I connect this geometry to the first input and our activator to the second. You have to be careful here because you have to specify now the active attribute, because by default it will not activate this. And let's see, I like to have some some visualization for the points here. What I do here, I just do here add sub as only for visualization, and I delete everything, but I keep the points here. And what I do here also, I create the color, and I set the color to ramp from attribute, which attribute I like to show is active. And let's do this white to red. That means red is active and white is inactive. And you see if you play now, I just disable my simulation. It's looking like this, but our radius is very, very big. You have to just go to condition, and maybe I just go here somewhere and change this here. You see now we specify the area for activating. If you want to have more distraction, you can do more or less. It depends on this parameter here. Okay, great. Now we have the active attribute. Let's see what's happened if we just put it here. The problem will be, you see the pieces are activated, they will fly and they will just stuck in the air. Let's see, maybe this will be something that you like to have, but normally it's not the case. Let's see, let's go back. Don't forget to activate your simulation, and let's see. I have something wrong here. Let's see what's going on here. Attribute transfer. Now we have our active name. Okay, I just look what's happened here, because anytime I just disable this, it makes some silly thing here. Okay, I'll come back to you when I fix this. Okay, this was everything fine. You have to just click here with a control to just refresh the cache here. And now you see what's happened. It's activated, and now you see you have something like this. If you like to have something like this, you can keep it, but let's do it better. Let's see how we can fix it. Okay, first I'd like to explain you the idea behind this, and then we will build it from scratch. I use here the solver. What the solver does is like a DOP network inside the SOAP, because everything here will be evaluated every frame. And what's great about this, we have the previous frame, and here we have the current frame. What I do here in attribute wrangle, I just grab with the point vex expression the active attribute from input 1 here, this is previous frame, of the incoming point, and then I just compare it with the current frame, and I take a maximum. For example, if our geometry is outside, our previous frame and current frame has an active set to 0. Then we move our geometry forward, and 1 point becomes the active to 1. We compare, our previous frame is 0, the current frame is 1, the maximum will be 1. Now it goes a little bit forward, and this point becomes a 0. What's happened here, the previous frame is 0, the current frame now is 0, the previous was 1, it takes a maximum, and it stays 1. That means once it's become active, it stays forever active. Let's create it from scratch. Okay, here is the solver. I put it here because I like to accumulate this transfer. You can write here accumulate or whatever. Go inside, create the wrangle. this previous goes to the second input, the current here, and let's grab the previous frame, the active attribute. This will be e at, sorry, not e, I just say integer, active or previous active, prev active equal, I use point expression, and I like to grab the point attribute, which attribute, active attribute, from which point, from a running point, and we already know the running point is I at pd num, close it. Now we have the previous frame here, and now I compare the previous to the current one, and I update my current one. I say here at active, or I at active is equal maximum from previous one and the current one. I just copy this guy here, and we have the current one. Okay, let's see how it works. Just go back here. You have to be careful with this guy because you have to always rewind and play here, or this reset simulation sometimes is doing some funky things. Okay, you see now it's activated and stays activated. Okay, great. Let's see what's happened now in our DOP network. Just go inside here and let's see how it works. You see now it's everything fine. These guys stay activated. Perfect. Now let's move on to our forces and how they work. I already prepared for you a couple values here. You see now we have here air resistance 0, 1, 0, 5, 1, and 0. And if you compare these values, you see this air resistance 1 looks like underwater, but you see the pieces just are coming to rest very quick. And the same thing happens to the spin resistance. Let's see if you... Now we have here the spin resistance. You see it's immediately stopped to spin, and 0, it's spinning and spinning and spinning. I will recommend to put a little bit of both, because you will get sometimes, not sometimes, always behavior that your little pieces never coming to rest. That's why it's very important to give a little bit of this both attributes or parameters. Okay, let's see how we can set it up. If you go inside your DOP network, we create now pop drag, sorry, not pop drag, and also pop spin drag. I connect these two guys to the merge, and I bring the merge to the post solve. You can also work with a pre-solve, but in this case I use the post solve because here will be no difference. Okay, and then you see this air resistance that you saw in Dailies here. Let's set it to 0.1, and also here spin resistance also 0.1. This is the values I already tested, but you can use your own. And now if you look on your simulation, you'll get a little drag here. You see. Okay, great. Now let's see how we can cache this proxy geometry as a point, and then use this point simulate data or cache data for moving our high-res geometry. Let's see how to do this. Let's create DOP import, and let's drag this DOP network inside the DOP network, and the object we'd like to use, just take this star away, and the object I like to have, this is the terrain, because we're interested only in this terrain simulation. And now you have to here import style. It's not a fetch geometry, because now it's giving you the simulation. But I like to have a points, because I don't want to have any geometry, because it's wasting time or wasting place of my drive. That's why I use the points, and my points now representing my simulation. Let's just cache them. You see these points have only these attributes. Let's just steal this guy here. I just copy this. I put it here. And we'll say here ground points. You have to be careful here, because by default, I don't know why it's not changing to $or $s. You have to change it, otherwise it will just override your ground high-res cache. Just put here $or $s. And this is time dependent. In this case, if you have some supervisor, or you like to have some dailies, you have to put the version here. And now I like to cache it. I cache it and I'll come back to you in a minute. It took about 21 seconds on my machine. Now you see we have this cache. And let's see how we can transfer this cache data to our high-res geometry. What I will do here, I will use transfer pieces node. And you see we have here geometry to transform, and here are the template points. Template points we already have. And you see this node is based on a name. It's look for the name. If they are the same, then the point will move your high-res geometry. But in this case, we have our name only on the proxy. What you have to do, you have to just copy this guy here, these two guys, with holding Alt, and connect the high-res geometry to your, or the high-res cache to your nodes here. And you see, if you look here, you have the same amount of points. You have to be careful. If it's not equal, then you did something wrong here. You see on these two guys, you have the same names, because it's based on the point number. And now what you can do, you can just bring this one to your high-res geometry. And now let's see the result. Just play. It will take a little bit more time. I come back to you when it's, you see now we have this. And as you see here, we have high-res geometry doing the same thing what the proxy does. Okay guys, now you see how this instruction works. And for the conclusion, what you learn now, how to set up RBD packed objects, ensure unique names on points. You already know why on points. We also exploring the physical attributes or properties of the fractured object. We simulated the proxy object, then we will just transfer our proxy simulation to the points, and from points to the high-res geometry. As you continue to the part 2, you'll build concepts, adding debris to your scene, bringing even more details and realism to your work. Okay guys, thank you very much for watching. If you like this tutorial, just subscribe and I'll see you in the next one. Bye.